Good morning, students. Yesterday we discussed Roche's theorem. Today we'll discuss some problems based on this theorem. So the first problem is find the roots of the equation z is to the power 8 minus 4 into z is to the power 5 plus z square minus 1 is equal to 0. Lying inside the unit circle having the equation z mod is equal to 1. To find the roots of this equation, we will use Roche's theorem. According to Roche's theorem, if we have two functions f and g which are analytic inside and on a simple closed contour such that mod of g is less than f mod, then function f and f plus g both have same number of zeros inside C. So let us break this left hand side into two parts. One of the part we have taken as the function f, which is minus 4 z is to the power 5, and the second part we have denoted by the function g, which is z is to the power 8 plus z square minus 1. Now we can see both of these functions being the polynomial functions, they are analytic functions within and on this circle. Now let us check the mod of g should be less than mod of f. So let us find the mod of both functions one by one. So mod of function f, that is 4 because z mod is 1. Now mod of function g, by triangle inequality this will be less than or equal to z mod raised to the power 8 plus z mod raised to the power 2 plus 1. Z mod is 1, so that will be 1 plus 1 plus 1, so that will become 3. It means mod of g, that is less than or equal to 3, mod of function f, that is 4, so we get mod of g is less than mod of f. So the conditions of Roche's theorem are satisfied. So according to that theorem, the function f and f plus g both have same number of zeros inside this circle. Now the function f is minus 4 into z raised to the power 5. So that has 5 zeros inside this circle, and therefore the function f plus g, that will also have 5 zeros inside this circle. Thus we have obtained the zeros of this equation, roots of this equation inside the unit circle. Now the another problem based on this, prove that the zeros of the polynomial z is to the power 7 minus 5z cube plus 12 is equal to 0 lies between the circles z mod is equal to 1 and z mod is equal to 2. So first of all, let us consider the circle z mod is equal to 1, and let us break this part into two functions. One of the functions we have taken as 12 and another we have taken as z is to the power 7 minus 5z cube. Now this being a constant function, that is analytic function, and this being a polynomial function, that is also analytic function within and on this circle. Now mod of the function f, that is 12, and mod of function g, by triangle inequality here, this will be less than or equal to z mod raised to the power 7 plus 5 times z mod raised to the power 3. Now z mod is 1, so this will become 1 plus 5, that is 6. It means mod of g is less than or equal to 6. So we can see from here that mod of function fz, that is 12. So mod of g is less than mod of the function f. So all the conditions of Roche's theorem are satisfied. So we can say that function f and f plus g both have same number of zeros inside z mod is equal to 1. But function f has no zeros inside the unit circle because that is constant function. So it means the function f plus g also have no zeros inside this circle. Now let us consider the second circle having the equation z mod is equal to 2. Now let us again split the polynomial into two parts. One of the parts we have taken as z is to the power 7 and second we have taken as minus 5z cube plus 12. Now mod of this function, that will be z mod raised to the power 7, z mod is 2 raised to the power 7, that will be 128. Now mod of g, by triangle inequality here, this is less than or equal to 5 into mod of z raised to the power 3 plus 12. We can see that mod of function g is less than mod of function f. So by Roche's theorem, the function f and f plus g have same number of zeros inside the circle z mod is equal to 2. Now this function has 7 zeros inside the circle z mod is equal to 2. Therefore, the function f plus g that also has 7 zeros inside the circle z mod is equal to 2. Thus we have shown that the function f plus g has no zero inside the circle z mod is equal to 1 but has 7 zeros inside the circle z mod is equal to 2. So these were some of the examples based on Roche's theorem. Now our next topic is meromorphic functions. What is meromorphic function? A function is said to be meromorphic function in a region if it is analytic in that region except at finite number of poles. It means a function is said to be meromorphic function if its only singularities are poles in the finite part of the plane. For example, rational functions. The function 2z plus 3 divided by z square minus 3z minus 4. If you find the singularities of this function, those are given by putting this denominator is equal to 0. And if we put this denominator is equal to 0, we get the singularities 4 and minus 1. So we can see that this function has only two poles. And so by definition, this function is meromorphic function because this function has poles at its only singularities in the finite part of the plane. Now, next theorem is to find number of poles and zeros of a meromorphic function, the relation between the two. Let us take a function f which is analytic inside and on a simple closed contour C, except for a finite number of poles inside C, and this function is non-zero on C. Then we claim that 1 upon 2 pi iota integral f dash upon f over this closed curve C is equal to n minus p. Here n is the number of zeros and p is the number of poles of the function inside the closed curve C. Now to prove the theorem, suppose function f is analytic within and on the closed contour C except at a pole z is equal to a. Let us take order of this pole is p, and suppose the function has a 0 of order n at the point z is equal to b. Now let us draw two circles taking a and b as centers. Taking a as center, we have drawn the circle C2, and taking b as center, we have drawn the circle C1. These are two non-overlapping circles inside the closed curve C. Now we have 1 upon 2 pi iota integral over C f dash upon f, that can be written as 1 upon 2 pi iota integral over C1 of the function f dash upon f plus 1 upon 2 pi iota integral over C2 of the function f dash upon f. Now, because we have taken the function f has a pole of order p at the point z is equal to a. So by definition of pole of order p, the function f can be written as g divided by z minus a whole raised to the power p, where this function g is analytic and non-zero on the circle C2. Now let us take log on both sides of this equation. This will become log of function fz. Here this will become log of the function g divided by z minus a whole raised to the power p. Log of m by n, that becomes log of numerator minus log of denominator. So this can further be written as log of g minus p times log of z minus a. Now let us differentiate both sides with respect to z. This will become derivative of log fz, that will be 1 upon f into f dash. Log of g, that will be 1 upon g into g dash. Here minus p is constant, derivative of log of z minus a is 1 upon z minus a. Now taking integrations along the closed curve C2. So integral over C2 of the function f dash by f is equal to integral over C2 of g dash by g minus integral of 1 upon z minus a dz. P is constant. Now because the function g is analytic function and non-zero, derivative is also analytic. So this whole function, that is analytic function inside and on the circle C2, and therefore by Cauchy's theorem its integral will be 0. So this integral vanishes, and the value of this integral, that can be obtained by using Cauchy integral formula. So by Cauchy integral formula, if a function is analytic in and on a closed contour C and a is any point within that contour C, then f of a is equal to 1 upon 2 pi iota integral f of z divided by z minus a dz. We can use this formula here. Here function f is 1, so our value will become 2 pi iota. We are having this value here. The value of this integral will be 2 pi iota. So our expressions becomes minus p into 2 pi iota. Now we can use the definition of a 0 of order n, because we are having the function f has 0 of order n at z is equal to b. By definition of 0 of order n, function f can be written as z minus b whole raised to the power n into phi z. Here phi is analytic function which is non-zero within and on C1. Now again let us take log on both sides and differentiating. We get f dash upon f is equal to phi dash upon phi plus n upon z minus b. Now let us integrate over the circle C1. This will become integral over C1 f dash by f. This will become integral over C1 phi dash by phi plus integral over C1 of the function 1 upon z minus a, and is constant. Now again this function phi dash upon phi, that is an analytic function, and therefore by Cauchy's theorem this integral will be 0, and value of this integral is again obtained by using Cauchy integral formula. That will become n into 2 pi iota. Now let us substitute the values from the equations 3 and equation 5 in the equation number 1. So we get 1 upon 2 pi iota integral over f dash upon f is equal to n minus p. Now till yet we have considered one pole and one zero at the points a and b. In general, if we suppose the function has pole of order pm at the point z is equal to am, and the function has zeros of order nm at the point z is equal to bm. Let us take there are r poles and s zeros inside C. This type of construction is possible because poles and zeros are isolated. So in that case our equation will become 1 upon 2 pi iota integral over C of the function f dash upon f is equal to summation nm n varies from 1 to s minus summation pm, where m varies from 1 to r. This is the total number of zeros and this is the total number of poles. So we have proved that 1 upon 2 pi iota integral f dash upon f over c is equal to n minus p. So this completes the proof of the theorem.